continuously there, and then he's now a very important professor in strongly correlated electron system, at least for me. Okay, so today he will talk about heterostructure and interface of quantum materials. So when you look at the quantum materials, then one may wonder what is quantum materials? So then, yeah, okay. So let's welcome Professor Lin.
Hello, can you hear me? No, I guess not. Can you hear me? Good. Okay. As usual, that I would like to thank organizer to give me this opportunity to present something. And actually, when I received the invitation, I was considering 2 points. One is that what subject should I give? From this cartoon, that actually this is some of the plot that I have been doing. This is the ion-based superconductor, and this is some low-dimensional magnetism, and these two are related to today what we are going to talk about, the heterostructure and the interfaces. Then I consider that in the very near future, once we get some more progress on this subject, that we might need the help from both Professor Choi Ah-ping and Professor Zhu Mingwu. So I decided to talk a little bit about this subject. Second thing is that eventually I realized that this is the curriculum for many joint institutes. So I really intend to make it a curriculum. And we just make more introduction or description rather than go to the technical details. And I would also try to try to finish that within 1 hour. So let's see if I can keep my promise. The subtitle, or actually another title of my today's subject would be actually create and search for quantum matter or quantum material. So the issue would be the first issue would be what is the quantum matter or quantum materials. So this is my definition. I would say that quantum matter or quantum material is matter with properties absent or surpassing those in non-existing materials. Oh, and the second definition, equally important, is that the matter with entangled orders. These orders compete and or strongly interact with each other. Okay, this is what my definition of the quantum materials or quantum matter. I think some of them in this community also adapt these definitions. In this sense, actually, we can think about the Nobel Prize winners for the past few years. For example, in 2014, that these 3 gentlemen received the Nobel Prize winner, and everyone knows that the reason for their award is the blue light LED. And in the sense that about the first definition, that matter with property surpassing those in non-existing materials, certainly that I would say broadly speaking that blue light LED is a kind of quantum materials at that time, and this is also in the broad sense this prize also going to the field of the quantum materials. And also the Nobel Prize of this years, these are 3 theorists, and the reason they got the prize is because if you look into the page of this Swedish Academy of Science, then you will see this description that for theoretical discovery of topological phase transition and the topological phases of matter. And I guess not every one of you understand what this says. Okay, then there is an easier word to say. They reveal the secret of the exotic matter or material. Okay, so these two discovering new material or new matter with properties surpassing the existing known materials and reveal the secret of the exotic matter actually is also part of the theme that, of my research. So I would like to introduce this subject in a descriptive way to all of us here in a colloquium. So let's keep on. So how do you make a breakthrough? How do you make breakthroughs in this field of the quantum materials or quantum matter? You can either, it might be we can either that try to invent or discover a materials, a single phase materials, which is with the again very peculiar property or excellent property for people to do application or to study and stimulate people's curiosity. Or you can improve the existing material with a very special crystal growth technique. And I think, for example, for these two categories, for example, Professor Zhou Fangzhen's group in this building focus on these two points. And also that it is something with the device physics that you can have some advanced heterostructure design. Try to get something new from and something special from what we have known about this composite material. So let me just give some solid example of this point. Okay, this is one famous example that actually is the high temperature superconductor. I'm sorry. Every material is one new materials, and the TC become higher and higher, presumably. Or it belongs to a different category of new superconductor. This is the first category that you discover in new materials, and then try to find out that if there's any application, or if it improve our understanding of the matter. And of course, for this category, one important Nobel Prize was awarded in I think 1987 for the discovery of the high temperature superconductor. Okay, so this is also belong to the Nobel Prize class. And also that, for example, for the blue LED gallium nitride, the reason they eventually succeed in this subject is that first, they can grow very, very good quality of the gallium nitride. Secondary is that, not secondary, and for the second point is that they eventually invent an almost optimized heterostructure for the device to emit the efficiently emit the blue light. Okay, so for example, for this subject, it includes the improve the technique of the crystal growth, and also design and fantastic heterostructure to realize the purpose for the application and the realization and application of the LED. Okay. Actually, before this is a Nobel Prize win. This is a Nobel Prize laureate. He said that actually several decades ago, said that the interface is the device. At that time, he was talking about the semiconductor industry and the devices that we are now using. But I think it would be probably even more true for nowadays the device physics or the applied physics. For the interface, you have material A and B. We have already known that in several cases, if we combine the material A and B and form an interface, then several interesting could happen. For example, this cartoon present some of the scenarios. For example, charge transfer could happen, and orbital reconstruction, or proximity, or the Coulomb catastrophe. And there are so many more. And today I'm not going to talk about this. I'm going to talk about something even more strange. To go to the even more solid example, let me first just introduce a modern example of this heterostructure and the interface. This is the LAO and STO interface. What's special about this interface? Well, it's really quite bizarre. For example, because this is a insulator. This is another insulator. They are very much insulating. If you really do the measurement, that you would get a very large resistance at room temperature, and you go to the low temperature, you even cannot measure it because the resistance is simply just too large. But interesting is that you combine these two, it would form a two-dimensional electron gas, and which is conducting. As you can see that once you form a bilayer, and this is insulator, but you measure the whole thing. Actually, it is conducting. It behaves like a metal. And certainly this is very, very bizarre. And people would, since that time, people were asking, what is the reason? And you can imagine that this question and answer. This question is very difficult. So it is actually a still ongoing unsettled issue. That's why bring us to the next page. That's why Professor Jiunn-Yuan will publish such a wonderful paper very recently. Present a new mechanism for this bizarre conductivity from the combination of two insulators. And in this paper, he simply just drew out the most popular scenarios, like polar catastrophe. I will go into detail of what polar catastrophe is. This is actually the first scenario. I believe it is the scenario proposed in the original paper. Oh, by the way, you know this paper, well, not much, but I just checked it. It was just cited. This was a paper 12 years ago. It was just cited by more than 2,000 times up to now. And so you can see it is a very interesting paper, it is still an ongoing subject. And then so this was ruled out, and this was ruled out by this paper. And probably the mechanism, of course, it is the heat and lattice instability. Actually, if this is the true answer, because this question is difficult, so this answer is definitely not easy to understand. So even I have to admit that I do not know every detail of this paper. So later you ask question, I will simply just call out Professor Jiunn-Yuan to answer. And hopefully, maybe you already give a colloquium on this subject. Okay, so let's move on. 3 years ago, with the help of Professor Professor we also did something on the similar thing. This sample was prepared by my PhD student in Professor Jiunn-Yuan's lab, and we do not answer why this heterostructure is conducting, but we try to find a new way to manipulate the conductivity of this device. So the thing we do is that we put instead, in addition to this bilayer, we put a PZT top layer on it. And because PZT is an actual ferroelectro material, so once we can control the polarization, the direction of polarization in PZT, we can, for example, when the polarization is up, this device, okay, this bilayer is actually insulating. And when we switch the partition to the other direction, actually it become conducting. And certainly this would be this kind of manipulation of the conductivity of this bilayer could serve as one of the choice for the future information technology. But well, how, I mean, we simply don't know if it's going to be useful or not. We will wait for the future. And then the next bilayer or heterostructure I'm going to introduce is this YBCO LCMO system. And again, this is not a new structure. Okay. For example, as early as in 2003, people were building for this kind of thing. There's a reason combine. We know that this is a high temperature superconductor. This is a you can simply just consider it as a ferromagnetic materials. And what's the point to combine the superconducting material with the ferromagnetic materials? The intuition is that you know we know very well that there is a rivalry between the superconductivity and ferromagnetism. The reason is quite straightforward, quite intuitive. This is the we call so-called the order parameter of the superconductor. For why there is a superconductor? Because something inside conducting is not electron anymore and not hole anymore. It's so-called the Cooper pair. Let's take a simple view that consider the Cooper pair consists of two electrons, and these two electrons would pair in a way that their spin would be singular. In plain language, that this for the superconductor, this composite Cooper pair has two electrons, and the spin of two electrons is just opposite. Okay, this is for S-wave order pairing and for the D-wave pairing symmetry. There is a peculiar thing which is called P-wave. In this case, that the electron would pair parallel, but in the nature we really didn't find any. Well, probably one, but that one is in question. That so most 99.99% of the superconductor is either in D wave or S wave. So the spin of the electron of the spin of the electron in Cooper pair actually anti-parallel. But we also know if you don't understand the Chinese, I would apologize. But this is the simple view of the ferromagnetic material. The spin or the moment of all atom or the molecule actually are parallel. So that's called ferromagnetism and spontaneous without external magnetic field. You can see that this kind of pairing and this kind of pairing simply are just opposite. So that's why they do not like each other. And indeed, that when you put these two things, when you go back to this transparency, when this is the, you can see this is the TC of the bulk material for YBCO. When you combine these two things, once the ferromagnetism becomes stronger and stronger relatively, the superconducting temperature simply just go down. In a way, these two kind of order, superconducting order and the ferromagnetic order, do not like each other. They even compete with each other and want to kill each other. Okay, and so that's the main idea that. But we like conflict, right? In a way that in scientific community we like conflict and try to get something new from the conflict. That's the motivation to put these two things together. And as I have already tell you that this is not new. Okay, this has been for more than maybe 15 years, no, not 15 years, but more than one decade that people invent this kind of bilayer system. But recently, we found out that for this bilayer system, there are more subtle things happening that than we previously saw. For example, let me just skip this one. I don't think you want to worry about crystal structure of this one. Simply just know that it's a famous high temperature conductor, and this is the famous so-called corrosive magnetism, and what we use is the ferromagnetic phase of these materials. Okay, that's just, don't worry about the structure itself. And we can, we can fabricate this kind of bilayer. But we can fabricate a bilayer in a way that we have precision control of bilayer growth. This is a kind of so-called ring technique that we can see actually. You see, for each oscillation, it is that one layer has been growth. So when we grow the either YBCO or LCMO, you see that we can control actually layer by layer growth, which is that nowadays our technology now really can control the growth of the thin film on the substrate by layer by layer. I mean, we can control it to be 2 layer or 3 layer. Later we're going to talk about this in another materials. Okay, and also by doing so, we can also make some trick to have some buffer layer, and we can control how these two materials connect to each other. Then there's 2 termination. We can call one kind of termination called MNO termination. The other termination called LL termination. Okay, but these are all just detail. The thing is that, and then you can have a very nice TEM image with atomic resolution to see, in real space, really that the structure is what you expected when you make this make this thin film. Then we study the magnetic property of this this kind of sample, YBCO and LCMO, but with 2 kinds of connection. We call it, in terminology, we call it termination, 2 different kind of termination. Let's see. Then we use a technique. This spectroscopy study was taken in advanced light source at Berkeley. At that time, I was visiting there, so the sample was prepared in Taiwan, and I was visiting the LS, so we say that why not we started this by this technique. In a way, I also don't want to go to the detail of this spectroscopy, but this signal, okay, this signal basically represents some additional order in these materials, and some additional order in the real space. And it happened that later we see, and for this bilayer termination, you will see that actually when the temperature is going down, you will see some increase of this signal, which means that in this system, you have some new order happening with the decreasing temperature, and we can do the same experiment in the pure YBCO, and you will see nothing changed with the temperature. Okay. So when this kind of order happen, there are several order could happen, several transition could happen in materials. One is the structural phase transition, but we know that from this contrast experiment, we know that, and we already know that there's no structural phase transition of the YBCO, pure YBCO, throughout the whole temperature region. And but so this is definitely not a structural phase transition. But what can it be? So we measure the magnetization of this sample. So this is a magnetic data. We find out that there are magnetic transition happening in this sample, and presumably it is due to because LCM of this material is a ferromagnetic material, and for the magnetic magnetization measurement, that this is this actually represents some ferromagnetic transition, and this new order simply just coincident with the magnetic transition in LCM mode. Then you see that why bother? Because you have a magnetic transition in ferromagnetic materials, and you see some, even if it is a magnetic transition, then it's consistent with the magnetic transition, which is just fine. But you know, the thing is that for this technique, we can choose the order of the specific element we want to see. For example, in this experiment, the order what we are looking for is the order of copper ion. Okay, and so this order very likely come from the order of the copper, and we know that there's no structure-based transition, and it matches with the ferromagnetic transition in LCMO. So the only feasible conclusion we can come up is that actually this is some additional magnetic ordering of the copper. But just remember that copper is in YBCO, which is the superconducting material. And for this sample, the superconducting temperature is around 70 Kelvin. So actually, we see some ferromagnetic order, even it is a very weak order, that within the superconducting phase of this YBCO induced by this bilayer. Okay, and this is new. For another termination, actually you can see that we see nothing. So we made up 3 experiments, and we can distinguish no ordering and with magnetic ordering in copper. The emphasis is on the order in copper. So, and this is also verified by the first principle calculation. This calculation was performed by Professor Zheng Longtai in Tsinghua University, and you can see that for this MnO2 terminal, we observed the ferromagnetic ordering in superconductor, and indeed the calculation actually demonstrates that yes, it's possible that this order is come from the copper oxide plane. Okay, but there's no magnetic order in copper oxide chain, and for termination, experimentally we don't observe any additional order, and theoretical also say theoretical calculation also refer that or reveal that there should be no order. So the experiment and the theoretical calculation or the first principle calculation, if you don't like the term of theoretical calculation, are consistent in this scenario. So the conclusion is that we indeed observe the coexistence of the superconductivity and ferromagnetism in this type of the termination by this heterostructure. So you will see fine, which is fine. Then maybe there is a weak coexistence of the ferromagnetism and the superconductivity. So what? And this new yes.
So it's still D wave?
Pardon?
Is this the pairing still D wave?
That's I'm going to the next transparency. First, but let me answer your question first. That mainly it should be still D wave because the magnetic moment, induced magnetic moment, is actually only 0.024 magnet per copper. Okay, but once you have some mixing of the D wave and the ferromagnetic order, it is possible that you will induce some kind of P-wave superconductivity. And for the past few years, there's some new field that once you have the in nature, we do not have P-wave superconductivity. Okay, no material actually reveal the evidence of the P-wave superconductivity. But theory also tells us that all the simple idea was also that if you have some coexistence of the ferromagnetism and the D-wave superconductivity or S-wave superconductivity,